Hey there, welcome back. I'm going to talk now about Chapter 8. Chapter 8 is when we start getting into not bonding between atoms, but bonding between molecules. So, the basic concept is we've already covered what happens when, I don't know, let's say I have like SO2. How is this held together? Oh my gosh, it's S and O, and I think it has extra bonds, and I can't quite remember. That is an old concept. What happens when this is its own molecule, and then you have another molecule of SO2, and then you have another molecule of SO2, and let's say you have an entire bag full of SO2, how are these molecules going to interact with each other? And that is what we're going to talk about. So the high level um, concept here is called intermolecular forces, but before we do that, we're going to talk a bit about the bond types again and how they interact with each other. So, remember the three types of bonds. There's the covalent, which are polar and nonpolar, and the other one, which is metallic. So, we're actually going to reclassify these again into just metallic and then everybody else. So, metallic structures are interesting. So when you have a collection of metal atoms together, let's just say tungsten, because I really like the idea of tungsten. Uh, it's just a W, no? W. Now, every atom has valence electrons, and what happens to the valence electrons and how they form bonds is what's important here. When you have a collection of a metal, like let's just say this is like a block of tungsten, the electrons just float around. They're just like all over the place, and they're all spread out evenly throughout the sample. So if I have a cube of tungsten, the tungsten cube, and it has a total of 500 electrons, then these 500 electrons are going to be perfectly spaced out within my tungsten cube. They're going to be floating around, yeah, but it's like having a pool full of water, and it's instead of water, it's filled with electrons up to the brim. So they just kind of swim around. They don't really change density; they're just kind of hanging out there. Now, important to consider here is how many electrons there are per atom. So the way you figure that out is you can actually just look at the periodic table. I'm just gonna draw a brief one right here. So you know how there are group numbers, group, and one, two, three, four. Well, this group number is actually how many electrons are floating around uh, per metal atom. Of course, that only really applies like the transition metals because those are the only ones that do this, that do the metallic bonding. Uh, yeah, I think these do it too, but for the majority, the transition metals are the ones that do this because these guys are all the covalent bonds. We don't care about them, but these guys do the electron C thing. That's what's called the electron C model. And if you just look at their group number, like 3, 4, 5, 6, all the way to I think 12 or 13, you can tell, oh, that's how many electrons per atom are floating around in my substance. Pretty simple. So tungsten, let me pull up the periodic table here, is in group 6, which means for every tungsten that I have in my sample, there's going to be 6 electrons just hanging out. Now, if I wanted to see how many I had, I could just count all the atoms I have and then multiply that by the group number. So I have 1, 2, 3, 4, 5, 6, 7, 8. 8 atoms. And for every atom, I have 6 floating around, or 6 electrons floating around being shared. 1 for 6. And so I thus have 48 electrons in my electron C. Simple as that. Now, this is why metals have There are particular properties that they do. I'm sure when you're in middle school you learned all about ductility, malleability. They just kind of exist. It's a conglomerate. They don't have a lattice. They don't have any network. It's just sharing electrons like communists, filthy communists. Um, Now the difference between different metals, because some metals you can like hit and then it'll like snap and you'll be like, what was that? And others are like super super bendy and it's super easy to do it. So what's the difference? It's the strength. So they are ductile and they are malleable and everything because they don't have a shape, but the strength at which all these atoms are holding each other together does matter. So if you have smaller atoms, you will have a stronger like bond between all of them. They'll pull together stronger. So stronger is smaller and more valent, more electrons per atom. So when you have more electrons and you have smaller atoms, it'll be stronger and stronger. Which is why aluminum, which is all the way on this side of the table, yeah, so this side, it has a ton of electrons floating around, and what does it do? Oh yeah, and it's really high on the table, which means it's super malleable because it's holding itself together really, really well. Meanwhile, tungsten is really low on the periodic table and does not have a lot of electrons, which means you can break tungsten. Like if I had a rod, I could break it and it would fall apart. Why? It's because they aren't the atoms aren't strong enough, or the bond, the intermolecular force, isn't strong enough to hold them together versus the force I'm exerting on it. Even though if it was a much lighter force, it would do this. Anyways, that's it for metallic bonding. Let's move on to the interesting bonds. I personally think the metallic bonds are cooler, but I mean, this is not my course. So the other one is everything else. So the way other molecules interact with each other is that they form lattices through molecular, like, let's say like supermolecular bonds. Super in the sense that it's like it's outside of the molecule. And this can look like, I don't know, like diamond. You'll have molecule, carbon molecule, carbon molecule, carbon molecule, and they'll be connected to each other. Carbon molecule, carbon molecule, carbon molecule. They'll all be connected to each other in some shape or form, some geometry. That's why pyrite comes in cubes naturally. It's because they all form together to form lattices. I can just keep drawing like, yeah, they form lattices, and that's how they stay together. And the connection in the lattice is the intermolecular bond, the intermolecular force that holds them together. So, one quick concept to cover before we move on. Let's say that this is part of a structure. So let's say I have one molecule. If you want to know the coordination number, you just count how many molecules are connected to other molecules. Like, if given one molecule, how many connections does it have? Well, let's say this is the one we're looking at, the center one. We have one, two, three, and four. So coordination number equals four. And of course, it's not just gonna look like that. Like this bad boy is gonna have some connections. This bad boy is gonna have his own connections. But you can still see he has only four connections. One, two, three, and four. And you can keep going. Boom. One, two, and three, four. That's what it is. Every molecule is connected to four others. And that's the coordination number. It's not too complex. You'll probably just get a picture and be like, oh my gosh, that's what it is. Yeah, so that's all for bond types. I think I'm going to end the video there. It doesn't really get more complex when you're just talking about like the general idea of bond types. and the structures. Like one is a lattice, the other is the electron C coordination number versus how many electrons you have per atom. And yeah, you could just use the group number to figure out the electrons per atom. And yeah, I think that'll be it. I'm going to pause it and move on. In the next video, we'll be talking about band theory. Yay.